Good afternoon, everyone. Today I'll be talking about energy infrastructure systems, including buildings, grid, and their interactions. First, a little bit about myself. So for those who know me, I changed my last name to Sun. So my name is Qun Zhou Sun, and I go by QZ. And you can find my information on my homepage and my lab page. In terms of research, I have a lab called Smart Infrastructure Data Analytics Lab, and the lab was established in 2018 with support from Siemens. The goal of the lab is to develop predictive data analytics tools to be applied in buildings and grid, and we are using UCF campus as a living lab. So we are collecting data from UCF campus and buildings and grid. And also integrate the predictive analytics into controls and optimization to improve energy efficiency and security of both systems. And for teaching, I regularly teach two courses. One is the senior level power system economics, and the other one is graduate level course on data analytics in energy systems. I've been collaborating with FSEC. I have a second joint appointment with FSEC, and for projects, our project partners are Unreal, Siemens, and OUC. Okay. So smart buildings and smart grids are two most critical energy infrastructure systems. They are different, but they have many commonalities. They are both physical engineered systems. They have lots of sensors and data, and there are uncertainties everywhere. The uncertainties could come from the data itself or the modeling process or even human energy consumption behaviors. And then, so there are, common problems that are constantly tackled by researchers in industry. For example, both systems have a goal of improved energy efficiency. That's kind of the #1 goal. But at the same time, both systems have concerns of cybersecurity. And also the systems are very interdependent. So their interactions are interesting to look at too. Let's talk about the buildings first. So buildings are, again, a complex engineer system. It's governed by like thermodynamics and differential equations. And we are using, there are many physical modeling tools to model buildings. Here I'm showing one tool we are using here in our lab. It's called Modelica. It's a modeling language similar to MATLAB, but it's open source and object oriented. So for example, this is a building. This is actually a single floor, simple one floor building. It only has one thermal zone here, which is like a huge, it's a room if you consider that. And then it has different objects like the damper connect to the outside. And then the heating coil, cooling coil, and fan, and all the duct work. So to build a simple floor like this already takes quite some time. If we consider modeling R1, like research 1 in UCF campus, it's gonna usually take about like 2 to 3 months to do it. And this is not the only part. After we finish build the physical model, the more time-consuming part is you have to collect the real data from the field and then try to validate your model against the real buildings, which is more time-consuming. So that actually motivate us and all the researchers to develop different modeling methods. One of the most popular modeling method would be a purely data-driven one. So, for example, I'm showing this on the right-hand side is a causal-based Bayesian network. The reason we are using Bayesian network, there are other data-driven methods, but they are less intuitive. They are less interpretable. So Bayesian networks is a bit more interpretable compared to other data-driven method. In this one, it's dense fully connected networks. And it has 2 layers. And the first layer or the upper layer is the root cause layer, meaning that all the inputs could, come from the environment, and then human control settings, and also the system states themselves. So they collectively contribute to the observations. The second layer are the observation layer that has all the measurement data. So if we collect enough data, then we can train this network using commonly maximum likelihood estimation. And then given observations, then we can actually infer the states of different inputs here. The inference could be done using exact inference or approximate inference, but basically for these states, what happened is that usually we don't directly monitor them. So from the observations, we can infer the states of different components to see if there's faults or anything we need to repair, stuff like that. So the root nodes are basically the uncertainty, where the uncertainty come from. These are random variables. That's why the observations, we can consider them as dependent random variables too. Okay, so that's one data-driven method to model buildings. However, we know that we have been spending years to study the physics behind different engineered system. We don't want to throw that away. How do we leverage both physics, physical knowledge, and data? That's the question we're asking, and this project actually is funded by EDOE. So the project, so what we are doing here is proposing a physics embedded Bayesian network. Now you can see that this network compared to the other network, it's a sparse network, and it has different objects mimic what what are in the smart building. So now you can see, like, when you see different clusters here, they actually represent different components in the smart building. So here is a damper, and then you go to next heating coil and cooling coil, and then the fan and supply fan, return fan, and coming back. So the cool thing about this network is that you can actually using now we are looking this is the first step of our modeling. So we are using a linear Gaussian model that you can actually implement all the physical equations along this edges, so that the physical equation, differential equations that we have could be discretized and then put in these nodes or edges. And also in this network, we include the control server to represent the states of control server, which is interesting to look at because the cyber attacks could happen in this object, right? So the cyber attacks could happen anywhere in all the sensors or the control commands. And by doing so, we basically embed the physical equations and also tailor it for looking at cyber attacks, how to identify the cyber attacks by looking at the states of control server and the sensors itself. Talking about cyber attacks, that's actually the main theme of our DOE project. So what we are trying to do is to build one of the tasks is to build a cyber security testbed for the building. So this is the kind of schematic for the cybersecurity testbed. Our lab inside R1, we have the Zico CC, which is a Siemens building automation system, and we also have a few hardware, including thermostats and actuators inside our lab. So what we are trying to do is to connect the building automation system by using with the hardware by using BACnet protocols and KNX protocols, and then try to model the building, any building, not only R1, but any building using these hardware in the loop modeling. So the building itself is modeled by Energy Plus, which is a DOE open source software. You can model building behaviors, thermal behaviors, and energy consumption in Energy Plus by, and then we include these hardware in this simulation. So right now, the whole team, including Unreal, UCF, and UMass Lowell, are try to be working together and build this testbed. We have different tasks here. Unreal is in charge of building this emulated BAS and the building model that's including Energy Plus and Zico CC. And UCF, our team is in charge of building the detection and diagnosis algorithm, and also in charge of design attack scenarios, so that that are going to be applied, going to be supplied to UMass Lowell. UMass Lowell is in charge of replacing some of the devices with rogue devices to try to change the control command and sensor data using that rogue device. So eventually, we're gonna have 3 sites building cybersecurity testbed, and we're using R1 data for developing that model. And let's come back to the grid. So usually the modeling grid is not a problem because over many decades we have been developing grid modeling, which are very accurate. But one of the problem for a distribution system is its lack of measurements data. In transmission system, bulk transmission system, this is not a problem because usually bulk transmission system are equipped with many redundancy sensors. So there we can easily build KVL, KCL, branch flow equations, power injection equations, and then we can solve those equations with redundant data. Usually we need to use state estimation tools to estimate different states, including voltage, power flow. However, in distribution system, it's not the case. Usually distribution system down to residential commercial houses, and commercial buildings, they do not have a lot measurement. here is just a simple example. In this 4-bus system, you only have like one measurement, the substation current. And how do you just use that one measurement and estimate the rest of voltage and power flow? It's a totally underdetermined system. So what we inspired by building modeling, we can actually use the same concept of Bayesian network. Like given one measurement of this substation current, we can actually estimate the probability of each state. On the right-hand side, this heat map actually shows by doing so, we can output a probability distribution for bus 4 voltage, which compared to the ground truth has a pretty good coverage. So now let's tie the building and the grid together. We know that building definitely is dependent on the grid because buildings need grid to provide power. Okay, but do grid need buildings? The answer is yes, especially in this area of all the high penetration of renewable energy, including solar power. So when a grid is highly penetrated by solar power, the grid become a less reliable or more volatile. So usually previously, when we only have load, electric load, its patterns is pretty predictable. So what happened is that you usually just ramp up traditional generation units, like gas turbines or coal power plant, to counter that uncertainty. However, with solar power, it becomes much more volatile, and the traditional generating units have constraints on how quick it can ramp up and ramp down. So that's not a those are traditional generating units are not options anymore. What happened is we can simply we can either use batteries, which is good, but they're expensive, or we can simply use buildings to provide flexibility, right? So the buildings, when you change the set point of a building or because of the thermal inertia, the power could change quickly. However, the temperature inside the building do not change very quickly, and then the occupants usually don't even notice it. So this is one of our work. We are trying to use buildings to provide grid flexibility. You can ramp up and down by adjusting different set point of the grid of the building. So now you can see that, well, the building control is model predict control, so it has to be but the building itself is very nonlinear, so we have to first formulate into a convex semi-definite programming problem, so it can be
Lucy,
solved.
you need to wrap up in the next 1 minute.
Okay, sure. So this is, I have one last slide to show. So basically, by running these algorithms, we can actually see the buildings could provide flexibility to reduce power or ramp power and up and down, but they have a different flexibilities and different times. In the early morning versus morning time, you can see the flexibility contour map are different. These provide a guidance for building operators and grid operators. And then similarly, this is another building providing grid services. For wholesale power market, you have 5-minute energy dispatch signal and 4-second frequency regulation signal. So how to closely track these signals by utilizing building controls. That's what we are doing here, and our results showing very close track of the grid signals without with very minimal temperature deviation. Here it's just about 0.05 Celsius. And I think that's that, and this is my near-term and long-term goals, and we're gonna do demonstration in UCF campus buildings, and then long-term continue enhance the modeling and optimization. methods. And with that, and I thank you for listening.